Any general questions, problems, anything? Happy Recovery Day Eve. What is technically tomorrow? I mean, the OWL homework does not really have hard and fast dates, but I mean, technically Wednesday, I should say, not tomorrow. Because tomorrow is Recovery Day. But the Wednesday one is last week's, and then everything's pushed forward a week. It should be, I mean, I think I updated the calendar if you go look at the custom calendar. Any other issues floating around out there? Then back to equilibrium. Again, we saw with the good old sit-stand reaction how the equilibrium works, at least from a kinetic standpoint, right? It's a balancing of the rate of the forward and reverse reactions. We'll see a little later in March how thermodynamics plays into equilibrium. It's a somewhat different picture of the equilibrium, but it's equivalent, right? And ultimately, what it means for the reaction is that you can, for most reactions, go both ways, right? And so you never reach a state where you run out of the quote unquote limiting reactant, as we were calling it in the past, right? Instead, you reach a point where the concentration of all the species, meaning all of the reactants and all of the products, stop changing, right? Although again, as you saw, the sitting and the standing doesn't stop. It's just happening at the same rate, right? And so the reactants and products are constantly reacting, but when you've reached this state of equilibrium, the amount of everything has reached a steady state, right? And so it really changes the way we quantitatively look at the reaction, right? In the fall, you had a limited amount of stuff and something was going to run out, right? Now, that assumption does not hold. Stuff doesn't run out, right? Instead, you get to this point of balance. And since you have this point of balance, right, we define the, if you will, end of the reaction as the point at which you reach this state of balance, right? And that state of balance is related to the concentrations of the products and reactants, right? And it is summed up in what is known as the equilibrium constant. And so the equilibrium constant replaces the limiting reactant as our goal for any reaction, right? We keep changing the amount of stuff, not until you run out of something, but until you get to this equilibrium constant, right? And so it's a number, it's a target, right? It's a goal for the reaction, right? But it does change the way we view the reactions, and it is always products over reactants. And so as a result, I don't want to really define large and small because, as you'll see, it's not strictly just the products. There's stoichiometry involved, but in general, the bigger K is, right, the more like a limiting reactant problem it is, right? If you got a really big K, you mostly have products. If you have a really, really small K, you mostly have reactants, right? And so K becomes our goal. The good news is, unlike kinetics, right, I can write the equilibrium expression based strictly on the balanced equation, right? The orders of the reaction for kinetics had to be determined experimentally, right? The powers of the concentrations for the equilibrium do not have to be determined experimentally because they are just the stoichiometry, right? So in 3 minutes or less, you can become an expert at writing the equilibrium expression. And so, if my reaction, again, in totally generic terms, right, was A plus 2Bs goes to 6Cs, all of them are aqueous. As I had mentioned before, we're entering the aqueous portion of the course, right? It is products over reactants, but it is the products to their stoichiometry divided by the reactants to their stoichiometry. Please note two things, right? One, right, these are the stoichiometries. And also please note in the equilibrium expression, that is B squared times A, not plus, right? There's a plus up here, but this is multiplied, right? And so as soon as I have a balanced equation, I can write the expression, right? Now I'm going to have to do something to evaluate that expression, and that's what we're going to talk about moving forward, right? But in the end, this ratio is some number, right? We saw it for sit-stand, right? For sit-stand, it was 2, right? Or it was a half, I forget. I think it was 2, right? No matter what I started with, I always had twice as many products as reactants, right? For any reaction, that's what K is, right? It is really fundamentally some target number for the ratio of the products to the reactants, right? And for now, we'll leave it as just some number, since I cannot calculate the number based strictly on the balanced equation. That I might have to determine experimentally, right? And so if you don't like the A, B's, and C's, here's my favorite reaction, right? Production of steam from hydrogen and oxygen. Again, I've got a balanced equation. I've got stoichiometry. It is always just the products raised to their stoichiometry, right? Divided by the reactants raised to their stoichiometry. So in this case, the water squared over the hydrogen squared times oxygen. All right. And you are now 90% expert at writing equilibrium expressions. The only thing I really need to add to this, right, is that not everything has a concentration, right? In these two examples, I had gases. Gases have concentration, right? Either pressure or molarity works for a gas. The previous example, they were all aqueous, right? Solutions have concentration, right? Solids and liquids do not really have concentration, right? And so the only real exception to this method is that if I have a solid or a liquid, right, it really doesn't have concentration. It has what's actually known as an activity. But that activity is constant, right? If you're a pure liquid or a pure solid, right, your concentration doesn't change, right? A chunk of coal is a chunk of coal no matter how big, right? And so its activity is constant. As a result, if I have a solid or a liquid, it doesn't actually appear as a concentration in my equilibrium expression, right? It technically appears as an activity of 1. So this 1, right, is technically 1 squared, right? It's a liquid water, which has a constant activity of 1 squared, right? But since it's 1, the stoichiometry 2, 3, 4, it's always just 1, right? And so, again, basically, I just don't write the concentration of a liquid or a solid in my equilibrium constant. Only gases and aqueous species actually have concentration. And so, in fact, this is basically the same reaction, except I made liquid water instead of gaseous water, but my equilibrium expression has changed, right? Big K, which is the standard abbreviation for the equilibrium constant, is now 1 over the hydrogen squared times the oxygen squared, whereas if I'm forming gaseous water, now the product, steam, actually has a concentration, so it appears. Yes, no, maybe. Right, so a couple more quick examples. Again, here's a balanced equation. Sodium plus chlorine gas yields sodium chloride. Right, for those of you who don't like to write the states of matter in your balanced equation, you'll have to start, right, because that is a critical piece of information now when I'm trying to construct the equilibrium expression. Since the sodium metal is a solid and the sodium chloride is a solid, right? The only thing I see in my equilibrium expression is the chlorine, which is a gas, right? Again, technically, you know, there's a 1 squared in the numerator and there's a 1 squared in the denominator, but it's just multiplying by 1, so it doesn't change the value of anything. And if you want another example, right? Now these are all gases, so hey, they're all gases, they all count, right? Dihydrogen sulfate gas raised to the first power. There's an implied 1, of course, for stoichiometry, divided by the oxygen squared times the hydrogen sulfide. Right. And it is that simple or that complicated, depending on how you feel about it, right? But as soon as I have a balanced equation, I can immediately write the equilibrium expression, or as it sometimes gets referred to by you or me as a result, the K equation. Right, again, please note, we just had little k for rate constant, big K for equilibrium constant is not the same K. Right. And quite frankly, that is the next 5 or 6 weeks of our life, right? And if you follow my mantra that K is K is K is K, right? It doesn't really get any more complicated than that, right? But please note, there are sometimes subscripts associated with K. They don't change anything, not a thing. If it's an equilibrium problem, I approach it exactly the same way. My other big equilibrium saying is that all equilibrium problems have 3 parts. You will soon see that. The internet is your enemy here in the sense that you can go and find all kinds of prepackaged solutions to equilibrium problems. That's great, except if it doesn't fall into the special case that they calculated for you, the equation won't work. On the other hand, my foolproof 3 steps always work, right? Because all equilibria are basically the same phenomenon. There's a target ratio of the products and reactants for all reactions. I call that my equilibrium constant, right? The subscript is not meant to confuse, although it sometimes does. It is meant to provide additional information which may be useful, right? And so most of the next 6 weeks is talking about the reactions that go with the subscripts. Most of those refer to reactions. KF is a formation reaction, right? Complex ion formation. SP is a solubility product. A is for acid, B is for base, right? And KC and KP, right, are for units, right? Because here's the thing about K, which might not be immediately obvious, right? K does not have consistent units, right? Because it's stoichiometry dependent, right? If I actually put units in here, right? I've got molarity over molarity squared times molarity, which is 1 over molarity squared for units, right? If the stoichiometry were different, it would have different units, right? As a result, equilibrium constants are generally written as unitless, right? But they actually come in 3 flavors, right? Because there's 2 units that apply, right? Because I could have, for my gases, molarities, they exist. I could also have pressure, right? In fact, pressure is generally the preferred unit if you have a gas, right? But you could use either one. And that's really all my K, C, and KP are trying to specify, right? The subscript C doesn't really change what K is. It's just implicitly telling you what the units are. It has units of concentration, which for equilibrium is only molarity, right? I would never use percent by mass. I would never use molality. I would never use mole fraction. It's always just molarity, right? In the KP, the P is for pressure. Again, by convention, it is always atmospheres, right? And so there are technically 3 equilibrium constants you could write for any reaction, although only 2 of them ever exist. And what I mean by that is, right, it's a units thing dictated by what type of compounds are in the reaction, right? But you can't have a KP if you're not a gas, right? And so you don't always have a KP, right? You also could have mixed phase reactions where there are both gases and aqueous species involved, right? And so there's actually a third equilibrium constant, which is referred to as thermodynamic K, right? Where I use the preferred unit for the preferred state of matter. And so in this case, right, somehow or other, I mean, there's something invisible here, a liquid or a solid, but right, this square brackets implies molarity because this must be hydrogen aqueous, whereas this must be O2 gas. And so ideally my gases should be measured as pressures, and ideally my solutions cannot be measured as pressures because only gases have pressure. So they're measured as molarities. And so if you had a mixed phase reaction, you could have mixed units. And that's what thermodynamic K represents. Right. For any given reaction, you never really have 3 different K values. There's 3 different ones you could write, but usually either one of them doesn't exist because they're not all gases, there's no KP, or the thermodynamic K is the same as either KP or KC, right? For example, here's a mixed phase reaction. I've got sodium aqueous, which I'm reacting with chlorine gas to give me aqueous sodium chloride, right? In that case, right, it's sodium chloride squared over chlorine times sodium squared, right? But I have the option of writing all of them as molarities, right? Even though my chlorine's a gas, gases do have molarity, right? And so if I wrote them all as molarities, what I end up with is a KC. right? If I were to write them using their preferred units, I end up with K thermodynamic, in which case the gas, the chlorine, should be a pressure rather than a molarity. Right. But I cannot write a KP, right? Because again, the KP demands that everything be atmospheres, right? There's no such thing as the pressure of a solution, right? And that's what I meant when I said there's really 3 different Ks I could write, but generally speaking, there's only at most 2 that exist, right? Right? If everything's a gas, then you can write a KP. Of course, if everything's a gas, the KP is also the thermodynamic K, because the preferred unit for the gas is pressure, right? So again, there's technically 3 different Ks I could write, but again, in practice, there's only 2 different Ks I could have, right? If it's all gases, I could write them all as molarities, or I could write them all as pressures. All right, and so I have both a KC and a KP. All right, and so the subscripts will sometimes indicate units, KC, KP, KEQ. The other ones we'll see over the course of the next several weeks really just represent different reaction types. So it's giving you a hint as to what the balanced equation should be. But it fundamentally doesn't change what I do with the Ks ever. If it's an equilibrium problem, there is a K equation, the more technical term being equilibrium constant expression, right? And what I do with that K does not change from reaction to reaction, right? It's the target ratio for the reaction, right? The concentrations or pressures keep changing until I get to K. And so K really replaces the limiting reactant as my goal. And honestly, there's only really 2 things I could do with them. Right? I sometimes refer to these as the equilibrium of the first type or second type, right? Most of what we're talking about ultimately becomes the second type. Today, we will only be talking about the first type because I don't have any equilibrium constants yet to do anything with, right? The only 2 things I can really do with them is either calculate the equilibrium constant, right? I know what the expression is, products over reactants. If I have numbers for the actual concentrations of products and reactants, I can calculate my equilibrium constant number, right? Once I've calculated it, I know it, right? The equilibrium constant, as we'll see, is temperature dependent, but that's about it. Well, also technically probably pressure dependent, right? But once I've calculated it, it is my equilibrium constant at that temperature. And so the other thing I could do with it once I've measured it, right, is use it to know what the final concentrations of stuff will be in my reaction, because that number is my goal, right? The reaction keeps changing everything until you hit that proper ratio, right? And so there's really only 2 ways I could do it, right? I mentioned this last week, I'll mention it again, right? The only real trick here is I now actually have 3 different concentrations I need to be concerned with, right? We saw this a little bit with my integrated rate law problem last week, right? I have stuff I throw in the beaker at the beginning. I have stuff that reacts, and then I have the stuff I'm left with at the end, right? It almost isn't worth saying, but it's probably worth emphasizing, right? The equilibrium constant only relates to the equilibrium concentrations, right? I can throw whatever I want in the beaker. There's no magic ratio there, right? Typically, I have 100% reactants and no products, right? And so the equilibrium constant does not apply, right? But the reaction is always trying to get to that magic ratio. And when it does, right, I have the equilibrium concentrations, right, and my ratio is satisfied, right? As a result, I need to do sometimes a little bit of accounting for which concentration I'm talking about, right? The absolutely simplest possible problem I could have is this one, right? And I know what you're saying, simple, look at all those words. Well, as I'm fond of saying, right, if you have a problem that has a lot of words in it, what do?
You underline?
You underline this, you underline, circle the number. No, you read them all one at a time, right? It's funny, everyone has some kind of method to avoid reading them all. While you're reading them, it pays to underline, circle things, make notes to yourself, right? But in the end, it really shouldn't matter how many words I have. I read them one at a time, possibly one sentence at a time, and construct the problem from there. So, right, hydrogen and oxygen gas react to form steam. All that's really telling me is what?
It's all gases.
What?
It's all gases.
Well, they're all gases, but I mean, the whole point of that sentence is what? It tells me
2H2 plus O2 yields 2H2O.
right. It's telling me what the reaction is, right? Hydrogen and oxygen make water, right? And they're all gases because, again, states of matter count here, right? And then it tells me hydrogen and oxygen were mixed in a 2-liter flask at 450 degrees C. Okay. I always like to ask this question, although it's hard in Zoom. Why a 2-liter flask at 450 degrees C? I'm laughing because it's funny. No, anybody?
Because they said so?
Because they said so. Yeah. Well, in some sense, that's almost the right answer. I got to put them somewhere, right? They're gases. They won't sit in the counter, so I put them in a 2-liter flask. Why 450 degrees C? I don't know. Did you ever try to bake a cake at 100? Right? I mean, I'm doing a reaction. There are conditions under which I'm doing the reaction. All that's telling me is the conditions. I make a point of that only because part of the whole underline the numbers or circle the numbers, right? People want to use the numbers. Nowhere in this problem will I use the 450 degrees C. It's just my cooking temperature, right? But I technically need to know it because equilibria are temperature dependent, right? And then I've got possibly the most important sentence in the whole thing. After equilibrium was established, it was determined there were 3 moles of water, 1.2 moles of hydrogen, and 0.8 moles of oxygen in the flask, right? What that's telling me is how much there is of everything at equilibrium, right? And that is what I would need to know to calculate the equilibrium constant. And so it's not very surprising that the fourth sentence is, what is the equilibrium constant? Now, this is by far the simplest equilibrium problem we will solve. Other than possibly on OWL, you will never see another problem like it. Because honestly, all I got to do is, multiply and divide some numbers, right? But start simple, build higher, right? And I maintain that the same methodology works for all equilibrium problems. And so all equilibrium problems have 3 parts. And quite frankly, I construct the three parts without thinking as soon as I get the merest hint that it's actually an equilibrium problem. I will also say this 500 times in the next month. And so we should practice. When I say all equilibrium problems have, and point to you, you say, thank you, three parts. This becomes a test to see if anyone is paying attention, right? I wish I had a nickel every time somebody came to my office for office hours and said, I have this problem, whatever. And I say, well, all equilibrium problems, and I point and they go, are hard or something like that, right? If I say all equilibrium problems have three, and you don't come up with have three parts, you just weren't paying attention, because I literally will start every equilibrium problem by saying it, right? So all equilibrium problems have three parts. And so it's automatic. If I see a big K, I start constructing the three parts. If I see the word equilibrium, I start constructing the three parts, right? You could argue it's one part with two subparts. It's really 1A, 1B, 1C, because everything really descends from the balanced equation, right? The nice thing about my equilibrium, right, is that I get a whole lot of information just out of having the balanced equation. And so one of my other fond saying is all chemistry problems start with a balanced equation. That is triply true of an equilibrium problem, because my other two parts come directly from the balanced equation, right? And so once I write my balanced equation, I can immediately write the K equation, or if you prefer the more technical term, equilibrium constant expression, right? Because all that is products raised to their stoichiometry over the reactants raised to their stoichiometry. And so I can immediately write that. And then whether it's an equilibrium problem of the first part, or first type, or the second type, right, it really becomes just a question of evaluating what the concentrations are, right? And there is nothing that could be more helpful for that than an ice chart, because I do have multiple concentrations possible. Not so much in this problem, but in the second problem, you'll see, right? And so, right, that first sentence gave me the balanced equation. I don't even have to read the rest of the problem to immediately construct the equilibrium expression, right? It's water squared divided by hydrogen squared times oxygen, right? Technically speaking, it did not specify Kc or Kp, it just said equilibrium constant, so you could write either. We'll talk on Wednesday probably about how to go from one to the other, right? In this case, I did it all as concentrations, so I'm doing the Kc, but you could have done it all as pressures. And so automatically, once I have the balanced equation, I write the K equation. And quite frankly, automatically, once I write the balanced equation, I start constructing the ice chart. Again, we used these in the fall a little bit. You resisted them. The time for resistance is over. It will really simplify your life. It's not really necessary in this particular problem because of the information I had, but since I insisted all equilibrium problems have three parts, I might as well stick to my guns here, right? Because again, there are technically three different amounts in any reaction. There's what you start with, there's what you finish with, and there's the amount of stuff that reacted in between, right? That is all the ice chart is really trying to say, right? Right. It's in some sense just a spreadsheet. It's keeping track of things, right? You know, it's shopping. I go to the mall with $100. I spend $20. What do I go home with?
$80.
$380 because I knocked over a little lady and took her purse on the way home. No, Yeah, $80. I mean, I had $100. I spent, I'm sorry, that was dark. And I should have issued a trigger warning. Right, $100 minus the 20 I spent leaves me with 80. Right, that's all it's really saying going down. There's really a vertical property and a horizontal property to my ice charts. Right, and vertically, it's really just a spreadsheet. What I start with plus the change, if I spent $20, it's minus 20. If I made $20 or I apparently stole $20, it's plus 20. And the equilibrium amount, the final amount is just what I started with plus the change. Right? And so in some sense, right, it's just accounting, right? And you know, that alone would be useful in the sense that I have a whole bunch of different things I need to keep track of, right? The one added complexity to my equilibrium problems that wasn't true in the not so distant past when everything was a limiting reactant problem, right? In a limiting reactant problem, I run out of something. And that's the only thing I really need to care about, that and the thing I'm making. Because the equilibrium depends on everything, right? I always need to know the final amount of everything. And so I have no choice but to care about everything. And so the ice chart, if nothing else, labels things for me. I've got the hydrogen in one nice, neat column. I've got the oxygen in one nice, neat column. And I've got the water in one nice, neat column. And so if nothing else, it's a way to organize, right? But the real power of my ice chart comes from the horizontal property of the ice chart, right? Which is, it's not three separate columns doing whatever they want, right? It's a coherent chemical reaction, right? This is where my shopping metaphor would break down, right? I started with $100, you start with $100, I spend 20, I have 80 left. How much did you have left? I don't know, right? Negative $300 because you had a credit card, right? $100 because you spent nothing, right? Because what you spend has nothing to do with what I spend. On the other hand, if we're playing poker, right? If I start with $100 and finish with 50 and you start with $100, you're going to finish with 150 because the money keeps moving around the table. And yes, I'm ignoring the VIG, right? In a reaction, the stuff keeps moving around the table because you can't make water without losing 2 hydrogens and 1 oxygen and getting 2 waters. And so what ties this thing together and makes it very powerful is that the change is always just the stoichiometry. And so my 3 columns are not independent. They're changing coherently, right? But they're only changing coherently, right? As we talked about a little bit last week, again, with that integrated rate law problem, stoichiometry really only applies to the stuff that's reacting. I can start with whatever I want. There's no restrictions. I can end, right, with the equilibrium amounts that don't have to be the stoichiometric amounts. If I've got a giant equilibrium constant, I might have mostly water and almost no hydrogen and oxygen. What I don't have is 2 hydrogens for every oxygen, right, and 2 waters, right? And so my ice charts become very powerful ways to both keep track of what's going on in the reaction and actually to simultaneously solve for multiple things, right? As you'll see shortly, right? Those aren't 3 different X values, right? It's the same X in every column, right? And so generally speaking, even though I've got 3 things I need to keep track of, right, most of the time there's really only one thing I have to find, right? In this case, I don't even really need to do that, right? Because of what's really the magic phrase here, which is that after equilibrium was established. And so quite frankly, I don't even know the initial amounts here, right? And in fact, I don't have any unknown. That's why I said ultimately this is the simplest equilibrium problem we'll solve all year, right? It told me what the equilibrium amounts of all three things were, right? After equilibrium was established, there was 1.2 moles of hydrogen, 0.8 moles of oxygen, and 3 moles of water. Right. And so if I wanted to evaluate the equilibrium expression, and that was my goal to calculate K, there's the numbers. Because when I was at equilibrium, that's how much of everything I had. Right. The only thing I need to do is get the units right. Because it gave me the amounts in moles. Right. The only thing that can ever go into an equilibrium constant is either pressure or molarity. Right. In this case, I chose to go with molarity because, frankly, it was easier and it didn't really matter. And so the 2-liter flask suddenly matters because my 1.2 moles of hydrogen is in a 2-liter flask. So, in fact, the concentration, the effective concentration of hydrogen is 0.6 molar. The effective concentration of oxygen is 0.4 molar. And the effective concentration of water is 1.5 molar. Right. My second part of my equilibrium problem was writing the equilibrium expression. All I got to do is plug in the equilibrium concentrations. Right. So 1.5 squared over 0.6 squared times 0.4 gives me a magic ratio of 15.63. Right. And again, because that was all done at 450 degrees C, that is technically the equilibrium constant at 450 degrees C. And so if I want to do that reaction again at 450 degrees C, right, I now have the equilibrium constant, which I could use on Wednesday, right, to determine what the equilibrium concentrations would be, right? Again, please note, it has to be molarity or atmospheres. It cannot be strictly moles. And this is where, again, some people have a tendency to interpret capital M as being an abbreviation for moles. It is not, right? Big M is molarity, right? Again, there are technically units there, but since the K units are not consistent, right, they are generally written as unitless quantities, right? In some sense, my units are all embedded in my subscript. Yes, no? No. I mean, it's stoichiometry dependent. So, right, I mean, right, if this is, you know, to the 5th power, right, it's going to make this much bigger for the same essential position. So, right, here's a similar but slightly different problem where I actually need all 3 parts, right? For simplicity's sake, same reaction, hydrogen and oxygen will react to form steam, right? Now I did do something different here. 4.36 grams of hydrogen and 28.6 grams of oxygen are mixed in a 2-liter flask at 250 degrees C. And then there's my famous phrase again, after equilibrium was established, it was determined there were 6.6 grams of water. Same question, what is the equilibrium constant? This time at 250 degrees C. Again, I see the word equilibrium twice. I don't even need to finish reading the problem because all equilibrium problems have 3 parts. The first and most important part is always the balanced equation because the other 2 parts really come from that. So same balanced equation here, which of course leads to the same equilibrium expression, water squared over hydrogen squared times oxygen. In this case, I really do need my ice chart because unlike the previous problem where I was just handed the equilibrium amounts of everything, in this case, I was not, right? I have an amount of hydrogen, I have an amount of oxygen, I have an amount of water. They're not all at equilibrium, right? The 4.36 grams of hydrogen was the initial amount. The 28.6 grams of oxygen was the initial amount. The only thing I knew about the equilibrium is that I had made 6.6 grams of water. Right. And so those three amounts did not exist at the same time in the beaker. Two of them were at the beginning, one of them was at the end, right? And so my ice chart here is helpful in sorting things out, right? If I convert those to moles, because, hey, moles is always better than grams, right? My 2.16 moles of hydrogen was at the beginning, so I put it in the initial box for hydrogen. The 0.894 moles of oxygen was at the beginning, so I put it in the initial box for oxygen. The initial amount of water is implicitly 0. Why do I say that? Didn't mention throwing water in the beaker. So either there was none, or it's a hopelessly flawed problem with no solution because I threw water in there and didn't tell you. And of course, that would never happen. All right. Right. I mean, if it's not mentioned, there probably isn't any. Right. I mean, you know, if you're making a cake, it doesn't say throw 6 eggs in there, you know, 2 cups of flour, a cup of milk, and don't throw raisins in there. Right. You never mention the thing that's not in there. And so implicitly, there's a 0 for the water, right? After equilibrium was established, I had the 0.366 moles of water. So that goes in the intersection of equilibrium and water. And so, hey, I filled in almost half my boxes. All right. Could have filled in before I even the problem. Right. Because ultimately, the change box is just the stoichiometry. And so quite frequently, I will fill in the change line before I even start doing anything with the actual amounts of stuff, because it's really just a relative amount. Minus 2x for the hydrogen, because I'm reacting the hydrogen. I assume the reaction to go left to right. It's minus 1x of oxygen because of stoichiometry. There's 2 hydrogens for every 1 oxygen. And since I'm making water, it's plus 2x because, again, 2 waters, right? These are just the stoichiometry. And so I could have filled that in even before I started, and I usually do. And so that actually allows me to fill in the last 2 boxes, because I really never need to fill in all 3 boxes in a column, right? Because I have my very useful vertical property, right? That I plus C is always E, right? So if I know I and C, I can get E. If I know I and E, I can get C. And so, at least symbolically, right, I can fill in the last 2 boxes, right? My initial amount of water is 2.16 moles. 2x of it is going to react. That would leave me with 2.16 minus 2x. I don't have a number for that, but at least I have an expression for that, right? In the case of the oxygen, it's 0.894 minus x. Again, I don't have a number for that, but at least I have an expression for that. But if I look at the third column, technically it's 0 plus 2x equals 0.366. That is a solvable algebraic expression, right? 2x is 0.366, right? And again, it's the same x in every column, right? Because x is just the amount that's reacting. They react in synchronicity, right? And so if I know X in any one column, I know X in every column, right? And so it's 0.183 everywhere I see an X. That actually gives me the equilibrium number of moles of everything, right? And that in some sense is the power of my ice chart. Solve for everything by finding that X, right? And I'll leave you there, right? Obviously, if I want to calculate the K, I need molarities instead of moles, but that's just a 2-liter phenomenon, right? And we'll pick it up on Wednesday after the recovery day when I'm going to try to grade 500 essays. I'm not going to do it. I can only do about 8 per hour, so start to do the math. Hopefully by next week, everything will be done, just in time for you to turn it into Sprint 2. Anyway, if you have questions or problems, I am still here. If not, have a happy Monday and a relaxing recovery day.
Thank you, Professor.
Take care.